so it's okay. We're gonna try a couple of little tricks with gravity today. So remember how I told you guys that the force of gravity on a planet is equal to, I'm going to prove that the force of gravity, or actually I'm going to show us how to actually calculate acceleration due to gravity, like how we actually get the g value. So we know that whenever we when we're on the surface, that force of gravity is actually equal to mg, right? Using Newton's second law, we know that this force is equivalent to a law of universal gravitation. So if we actually are thinking of ourselves as a certain distance away from the planet, we can get 9.8 meters per second squared by doing this. The uh, the force of our gravity on the surface of the planet, this mass times acceleration due to gravity, or really this is just ma. So like this is like the blanket version of mass times acceleration. So I could say this mass times this acceleration is equal to big G times big M times little m over the distance or the radius of the planet squared. And what happens is, just like always with these kind of situations, everybody brings mass to the party. The mass ends up canceling out. And if you wanted to find the acceleration due to gravity on any kind of planet, it's just g times the mass of the planet divided by the distance squared. And if we plug in these numbers, it seems far-fetched, but this 6.67 times 10 to the negative 11th times the mass of the Earth, which is, what is that, 5.9 times 10 to the 24th kilograms? I think that's right. You might want to double check me on that. And the radius of the Earth, I've already forgotten what it was. It might be like 6 times 10 to the 6th or something like that. Maybe I've got it over here. Let's see here. 6.37 times 10 to the 6th. 6.37 times 10 to the 6th squared. If you plug in all of those values, I bet you get 9.8 meters per second squared for the acceleration. Try it. Plug them in. See what you get. If it's not 9.8, I have some splaining to do, because I believe that should actually, that should work. That should work. It should work really well, actually. I'm gonna use my $5 rinky-dink calculator over here, see if it actually turns out, because I think some people are actually wanting to sabotage me here. 9.69. Did you use all the decimals, or did you just kind of like? Are you sure? Times, times 10 to the 24th. Yeah, he's really close to 9.8. Uh, divided by, let's see here, 6.37 uh, times 10 to the 6. Yeah, 9.7, right? Meters per second squared. Now, if you want the 9.8, you're going to have to use all of the significant digits that we know about the universal gravitation constant, the mass of the Earth, and the 6.37. There's other digits that we know. We just haven't gotten there. Oh, come on. You don't think 9.7 is close enough to 9.8? You know what? Fine. I'll just do this. Just going to go erase this and go 9.7. Are you happy now? This brings up a whole big conversation about significant figures that we're not going to talk about, because in AP physics, the sig figs don't, like, they say a sig fig is a mathematical argument on the precision of an instrument. So, like, for example, if it says 6.67 times 10 to the negative 11th, that means that you've actually used an instrument that measures out 3 digits of certainty. 6 and 6 and 7 are digits of certainty. The more digits you have, the more precise your instrument is. these values, if you take AP chemistry, go into a lot more significance. But what we normally go with, the general rule in AP physics, is you generally only use as many digits as you start with in the problem or what's given to you. So I see 2 and 3 digits here. So we normally just go with 2 or 3 digits and then we're done. So yeah. Yeah, so basically just don't like if you get an answer that's like 9.6238517216285, like there's no logical way that you are that precise with anything that you've done. Okay, so like even if we're using the lab quests and the motion sensors, you'd be lucky to get to the hundreds place on velocity. So why would you write those extra digits out? You shouldn't. Okay, so I mean, we've got 2 sig figs here. It's not a huge measurement. We can be happy with 9.7, I guess. But that is our trick on how to actually get that to work. Okay, I'm okay with that. All right. So that's my first trick for today is how to show you guys how you can actually find acceleration due to gravity using the universal law of gravitation. Okay. For my next trick, do y'all know how we actually found the universal gravitational constant? We just looked it up. Well, yeah, we take it for granted, right? Because like whenever we look at it, we're like, okay, yeah, G is equal to 6.67 times 10 to the negative 11th. What is it, kilogram? We did not compare two planets that are similar to each other. So, um, because and the main reason why we didn't do that is because the universal gravitational constant was found around 1800. Okay, which means that we didn't have this information about different planets. We in order to find that information about different planets, we had to use stuff like the gravitational constant to find velocities and stuff like that, because we didn't know necessarily what that force was out in the middle of the universe. Yeah, and there's definitely some old dead guy vibes coming around here on this one. What is that unit for the universal gravitational constant again? Newton, no, it's that, well, I mean, big G is like the letter. That's not the unit. It's Newton, let's see, meters squared per kilogram squared. And it's easy to remember because the two masses are on top, so they'll cancel out the kilograms, and the distance squared is on bottom, so the meters squared should cancel out, and your answer should just be left with newtons. Okay? So in about 1800, here's the experimental setup that this guy came up with. The old dead guy, do you care about his name? Okay, his name was Cavendish. Okay, Cavendish, and you've probably heard him from some other stuff before as well too. He might be on the history list of like 100 most influential people. I'm not entirely sure. He might be, but he found the universal gravitational constant, which allowed us to do all of this stuff. And here's what he did: he took a really, really big mass, like very large, several kilograms. Okay. And then he took a different mass that is the same intensity or the same mass on the other side, and he put a string that was held that holds a stick. Okay. And on this stick were two little tiny masses, and these little tiny masses were like right next to the big masses. And what happens is if you have this in a completely still room, these masses will actually start to this will turn the rod. So the rod will actually start to turn in a gravitational attraction towards each other. This is a very, 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 very small motion. So what he had to do was he couldn't actually just like measure the amount of rotation itself because it was so slow. It didn't actually make any sense to measure it. So what he did was he took a candle and he put a mirror on the string, and whenever the light would shine on, let's see, I'm going to use a red for the candle. See, these are fancy times. So he used a light, and whenever the light would shine, as the thing twisted around, it would change the angle that it reflected back. And he would look at how it progressed from one spot on the wall to the other spot on the wall, and he would record how long it would take that to travel over time. And what would happen is this thing would just like it would move, and then it would move back because they would start to twist the string, and then the string would get too twisted, and then it would pull back. So this thing would just constantly go back and forth, back and forth, back and forth, and he would measure the amount of time that it took to go in between that. And then using some fancy math, which we're totally not going to go into, he came up with the fact that, hey, the constant proportional force that this thing should have has a proportionality constant of 6.67 times 10 to the negative. I think he was close. I think he said that it was either like negative 11 or negative 10th power. So like he didn't like nail it, but he got real close. And as more people did more and more different experiments, they came up with finer values for it than 6.67. And if you look it up on like the International Standards website, it's got a ton of decimals that goes along with it. Every constant has like a ton of decimals, and people are constantly trying to get more and more precise as we move on through science, basically. Why do we want to get more precise? Because more precise means you can do more stuff with it. So like, no, that's not stupid. That's actually No, that's not stupid. That's something that is actually important. Engineers need that information. So like engineers don't do that information. Engineers use scientists to get that information, and they can use that stuff to make things. Totally. Absolutely. What's up? Yeah, typical engineer right there. Yep. Typical engineer. Okay. So, is that okay for this trick? I don't really think I need to go into too much more detail on that, other than like that's what they actually used, and that the two masses are gravitationally attracted to each other. You might see something similar to that show up maybe on an AP open response. I don't know. You never know how they work out these things. Um, every once in a while, I get lucky and serendipitously go over a question that's actually on the AP test. That's like one in a thousand, though. They come up with different stuff all over the place. Basically, yeah. All right. So I think we're gonna go for this next one. At what altitude is the constant g cut in half? Okay, at what altitude is g cut in half? So how high above the Earth do you have to get before the acceleration due to gravity is no longer g, but it's actually g over 2? How much of a height do we have to get above the surface of the Earth? So the first thing that we'll say is that, well, we know that the radius of the Earth is a certain value, so let's call that RE for the radius of the Earth. And we want to know, what's this altitude? What's this height? How far do we have to go up there? Okay, big brain time? Okay, I'm with you. Oh, the GMM over R squared? Right. Well, it's not just double, but I don't think that's what she was saying. I don't half the gravity. Right. Right. So like in this case, yeah, you're right. So like the distance here between these two things is going to be the radius of the Earth plus the height is what we're going to have to deal with, right? We're looking for this. We know what the radius of the Earth is, but we're looking for this. It might be a little bit easier for us to keep the radius of the Earth as RE instead of typing in 6.37 times 10 to the sixth. Because if I just type in 6.37 times 10 to the sixth, that's going to make things complicated. It's a lot of writing. Okay, so this is the actual distance that we need to worry about. That's true. So for all intents and purposes, we can call this d for the distance. Okay, we don't actually have to write it in as d. We can just write it in as re plus h, and I'm fine with that too. Okay, and we want gravity to be half. We're all tired. So, do we need the mass of the Earth for this one? It depends on how you do this. So, it really depends on how we want to set this up. If you want to do it my way, then you don't need it. If you want to do it your way, we might need it. But then you'll find out that it cancels out anyway. So, did you do it my way? You might not like my way. It's a very analytical approach. Are you sure? You're sure? Okay. So, it is well established that if we wanted to find the force due to gravity in normal circumstances, it would be that our mass times acceleration due to gravity is equal to the same thing as the universal gravitational constant, which is g little m big M over the radius of the Earth squared. Is that okay? And also, using the trick that we talked about earlier, we can just go ahead and get rid of these. So I know that g is going to be equal to g times big M over re squared, right? So, but this is for 9.8 meters per second, right? True story. If we're cutting that number in half, so if we're going to half of our surface gravity, so why don't we call this the GS for the surface gravity? How's that? Okay. And we're going to say that, well, the G that we're looking for is really half of the surface gravity. Okay. So basically, if we cut this number in half, what does this do to our equation? Okay. So I can say that, well, half of our gravitational constant, right? Half of our surface gravity is equal to what happens over here? Okay. So like think about this. What changes? Does gravity change? I'm sorry, does the universal gravitational constant change? No. Does the mass of the earth change? No. Does the distance change? Okay, what is the new distance? So this is going to be G big M, okay, divided by what is this down here? This is parentheses RE plus H squared. Okay. Is that fair? We okay with that? Okay. Um, then all we're going to need to do now is we're going to need to solve for the height. Oh no. Why is that H down there in the bottom? This is scary. Well, we have to because this whole thing isn't, look, isn't this GMM over D squared? Well, this is D. So I have to square everything. The RE and the H has to be squared. Okay, the radius of the Earth and that has to be squared. Okay, cross multiply. Okay, we can do this. This is going to get a little tricky. And there are probably some cleaner ways to do this, but this is where we are. So we're going to cross multiply. This is going to be half of GS times the radius of the Earth plus the height squared is equal to big G times M, right? Then, okay, that's fine. So we would have make sure this stays in parentheses, the radius of the Earth plus the height squared is equal to gm over the surface gravity. And then since the 2 is on the bottom, we're just going to go ahead and flip this back over to the top. So that'd be 2gm over little g. Okay. Now we need to square root. So we're going to take the square root of that. So the radius of the Earth plus the height, this is just going to be like the distance, right, is equal to the square root of 2gm over gs. Man, that looks familiar. It's like a distant relative or something. Yeah, so the height, it would be square root of 2gm over surface gravity minus the radius of the Earth. It does kind of look a little bit familiar. That square root of gm over, I mean, it's really similar to something we've done before. I just it's like a deja vu. I don't know. Maybe if we looked back up in the notes. Yeah, I think we have done that, right? Yeah, I think we did. Strange. It's like I was training you guys for something. I don't know. Okay. Well, I mean, at this point, it's just plug and chug. Now, this is not the most elegant solution to doing this, but as long as the algebra is correct, it should work. And it seems like it's legit. So we're going to need to plug and chug this stuff. So we're going to square root. Now, keep in mind, when you put this in the calculator, definitely square root at the end. So that's 2 times 6.67 times 10 to the negative 11th times, what is that, 5.9 times 10 to the 24th kilograms divided by 9.8 minus the radius of the Earth, 6.37 times 10 to the 6th meters. And that mess, emphasis on mess, should actually get you something. I do stand to note that on the AP Physics test, they would probably stop you here. They probably wouldn't make you actually type in the numbers, to be honest. Like you would have to derive an expression, and this would be the stopping point. Okay, but since we're here and I kind of want to know the number, then let's try to find out what that number is. That is not within the square root. Yeah, that is definitely not within the square root because it was over on this side, and then we're going to move it by subtracting RE from both sides, so it stays out of the square root. So I would get all that stuff inside the square root as a number, and then I would square root it as a separate operation. So I would type in, I'm going to get my rinky-dink calculator out, 2 times 6.67 e negative 11 times 5.9 e 24 divided by 9.8. And then I would take the square root. So I'm going to do square root of the answer. Helps if I actually hit the square root button. Hit the square root of that. Oh, crap. Square root, second answer. Okay. And then I'm going to subtract out 6.37 times 10 to the 6th power. All right, let's see here. 1, 2, 3, 4. Huh. Okay. Fair enough. We'll see what you'll get. 2.5 times 10 to the 6. 2.5 what? Just 2.5? It is meters, yeah. 2.5, but like the two digits are, you just got 2.5? Well, so if it's 2.59, do you think you might want to round it up for me instead of round it down? That would make kind of a difference, don't you think? Did I get a second on that? Anybody else got that? I think that's a good idea. So I'm just going to write down 2.59 2.59 times 10 to the 6th. Is that the same thing that I got? 1, 2, 3, 4. Yeah, times 10 to the 6th meters. For what? What'd I do? That's not my fault. Oh, you just want me to it's 2.59 times 10 to the 6th. So by our calculations and completely ignoring significant figures, we come out to 2,590 kilometers. So if you go that far above the surface of the Earth, you are at half of Earth's gravity. Okay, so that would be, let's see, 2,590. Um, that would be a pretty high distance. What is something that's 2,500 kilometers across? Maybe like the continent of Europe, maybe? No, it's got to be more than that. I don't know. I'll have to look that up. So what width from what? Yeah, is it actually giving you something? Oh, so from north to south, you'd have to go double that value-ish to actually like. Okay, so it's actually shorter. Yeah, north to south seems like you'd have to go that distance twice that way straight up in order to get half of Earth's gravity. So it's a pretty far distance away. It should be safe to note that like if you are above the Earth, it's gonna fall. Okay. it's not me. I promise. I didn't do it. Okay, okay. No threatening going on here. Uh huh. Uh huh. Uh huh. Uh-huh. Okay. Uh huh. Uh huh. Uh huh. There was right, right. Yeah, exactly. It's interesting. Um, okay. So I we can do one more thing because I think we've got time to cover escape velocity or at least kind of start about it. But it's going to require a little bit of knowledge from physical science. So we might have to go into a little bit of some like prerequisite knowledge. So, your escape velocity is essentially how fast you have to be going to yeet away from the Earth. So it's how fast, yeah, how fast you have to go. Or like straight from the surface. Like if you just like flat out had this velocity straight from the surface, you would leave, you would not come back. It'd just be like how fast you have to be going to escape Earth's gravity. Okay, to escape, escape. Mm-hmm. Correct. Yep. Absolutely. Okay, because usually we have a debt that we cannot repay, and that debt that we can never repay is the Earth's gravity. So we have an energy debt. It's not a money debt, but it's actually an energy debt. Because anytime you're trying to move away from the Earth, it costs you energy to be able to do that. And the main two types of energy that we really have to deal with are kinetic energy and potential energy. So that's where our previous physical science knowledge actually comes into play here, because there are different types of potential energy, but kinetic energy only has one big equation that goes with it, and that's that the kinetic energy is equal to 1/2 the mass of the object times the velocity squared. Y'all should have seen 1/2 mv squared before from physical science or physics. Okay, so if you've seen that before, then we're going to use it. Potential energy has many different forms, but we're going to be dealing with the gravitational potential energy, which is given the letter UG. This goes perfect with the caveman stuff. Okay, yes, UG. Okay, gravitational potential energy. We're going to use that. Who did? Yeah, right. And so I'm going to say that the gravitational potential energy is equal to mg H. Have you all seen that before? Okay, good. Mass times gravity times height. Okay, so like y'all should have actually seen this stuff before. Now there is a relationship between kinetic and potential energy. So if you spend kinetic energy, then that kinetic energy is going to have to be. No, no, I'm teaching right now. I'm not answering the phone. All right, so it's 1/2 mv squared is equal to mgh, and if you're dealing with like the Earth, what we're gonna do is we're gonna have to set up a situation. So like here's the Earth, and you're going to leave. So if you're going to leave, you're just going to like go out this direction with a certain velocity, and then eventually you'll just like you'll just leave. You'll never come back. Okay? So if we try to look at like our kinetic and our potential energy at that point, one of the good things about potential energy is we can always set like a zero ground or a 0 point. So if it said that UG was equal to MGH, we can set that value. We can just say that, okay, well, at this area, at like flat ground, we have zero potential energy. So I can say, like, at the bottom, UG is equal to zero. Do what? What's our problem? That's okay. It'll be fine. And our kinetic energy will be 100%. Okay, so all of our kinetic energy will be put into this value. Okay, now our life gets a little bit more interesting here because I think that we actually said that this mg a little bit earlier in our bag of tricks was equal to something. So like whenever we're no longer on the surface, we can actually substitute this mg value for something else instead. We, we can say that, yeah, big G mass of the planet over r squared, right? Okay, so that's going to be, so big G m over. Now this distance is going to become the distance that we're traveling out this way. So it's no longer the distance of the planet. So I'm going to call this h squared times h. Okay, which means we do get some cancellation here. So bloop, bloop, those get to go away. Okay, so our potential energy due to anything that's like not on this planet is the gravitational constant times the mass of the planet over the radius. Okay. Now I think, hang on, was that for mg or was that for just little g? I think we might actually need the little m guy too. Are you sure? Are you positive? I don't know if I agree with you. I think we might actually need to, I think we might need to actually keep this guy. Let's go back up. The good news is that we've actually got this recorded, so we can actually look back up and see what's going on here. It looks like our acceleration due to, oh crap, I went too far. Our acceleration over due to gravity is just g big M over d squared. The little m doesn't cancel out down here, so I highlighted too much stuff. Where'd it go? Oh no, it's gone. Where'd it go? I might have to close it back out and open it back up again to get it to show up. Oh, 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 there it is. Okay, whew. Okay, just potato computer is doing potato things. So let me try to rephrase that, make it sound a little bit better here. It's not the mg value, it's just the g value. So that g, that's not really even close to an m. It's okay. Potato, you can do it, potato. It's okay. So this g is, according to our little tricks that we did earlier, gm over r squared or h squared. So our formula whenever we do this should be gmm over r. That's our potential energy, okay? So when we eat away from the Earth, technically we're going to try to spin. This is the minimum escape velocity needed. So the minimum escape velocity, whenever we go out there, the kinetic energy is going to be equal to 0, and the potential energy is going to be equal to g m m, big M, little m, over r. Okay? Well, as it turns out, since there's no kinetic energy up here and there's no potential energy down here, that the amount of energy that you spent to yeet yourself away from the Earth has got to be stored in that gravitational potential energy. So they're equal to each other. Okay? They're equal to each other. So what that means is that well, I mean, this is just the law of conservation of energy, which we'll totally get into later, that says that the energy that you spent at the beginning is equal to the energy that you have at the end. So I'm just going to call it EI is equal to EF. So energy at the beginning is equal to energy at the end. What do we have at the beginning? We have 1/2 mv. How did I know you were going to do that? 1/2 mv squared. And then on the other side, we're going to have no, sorry, GMM over R. My bad. I almost put MGH. It's G big M little m over. You want to use H or R? Yeah, I know we haven't decided, obviously, because I just put H. We're going to use H. Okay, I'm going to put H over here, and we're going to put H over here for our height. But just remember that our height is going to be from here all the way out, okay? It's going to be from the center of mass of the planet. So now we can just solve for the velocity, and we realize that this time everybody brought mass to the party, so the mass does end up canceling out. But if I got rid of it, then that mass would still stay over there. So it's a good thing that we added it in. It's okay, fair, I guess. Weird flex, but okay. I'm not. I mean, you're not wrong. So okay. Yep, so if we take the square root of both sides and multiply both sides by 2, our escape velocity necessary to get away from a planet is equal to the square root of 2 times big G times the mass of the planet divided by the radius of the planet, which we're calling h. Okay, so that's the center from the center of the planet out. So, since we're dealing with a planet, we probably should have used R, but y'all picked H, so we'll just go with it. We'll stick with it and be fine. Okay, does that make sense? Okay. And then this is what you would need. Okay, so that means that if you have a more massive planet, then the escape velocity is going to get larger. If you have a same mass planet, but the height on or the radius from the center gets smaller, it's a more dense planet, it actually gets harder to escape from. Okay, so which I guess makes a little bit of sense. It's hard to think of like more dense planets, but they can actually occur. There are things that are more dense than rock and iron in the universe. Yeah, specifically hashtag neutron stars suck in everything. If you lead is super dense, yeah. Neutron star material is theorized that if you had just a teaspoonful of it, it would weigh as much as a semi truck. So like a teaspoonful of it would weigh like 10,000 pounds ish, give or take. So it's very dense materials. Do what? Just put some wheels on it and just like no. I mean, like if people had that, they'd start throwing it. Do what? Tungsten is very dense too. Yeah, I think the most dense material is osmium or iridium. I can't remember which one it is, but one of those two is very dense materials. They're right up there with lead and then some a little bit. So if you had like a planet made of lead, then that would be a more dense planet, and you would have a stronger gravitational field. So you could make the Earth out of lead, and it would technically fit in a smaller radius if you're using the exact same mass. Hopefully, we're not going to make a lead Earth, though. I don't think that's on our top 10 list of things to do. No, we don't. There's not enough lead out there. Yeah, like the amount of stuff in the universe just isn't that large to be able to. Or sorry, not universe. The amount of stuff on the planet Earth, we can't. You know, there's not that much lead in there. I don't know how much lead is on Mars. That's an interesting question that I don't have an answer to. You guys have any questions? You good? Um, I think we're, I think we're okay for today because we've got 8 minutes. What kind of ooblar are we talking about here? I'll just go ahead and